Welcome to Section 6, Lesson 5. Across the previous 4 lessons, we covered the 3 solving methods for linear systems and the decision rule for choosing among them. Today, we focus on the 2 special cases where the system does not have a unique solution, the no solution case where the system is inconsistent, and the infinite solutions case where the system is dependent. Each special case has a clear algebraic signature when you apply substitution or elimination, and a clear geometric signature when you graph the lines. Today we lock in both signatures and walk through the 2 cases with worked examples illustrating the algebraic and geometric perspectives together. First idea on the board. The no solution case occurs when the 2 equations represent parallel lines that never intersect. Geometrically, the lines have the same slope but different y-intercepts. Algebraically, attempting to solve the system by substitution or elimination produces a contradiction like 0 equals 5 or 0 equals -3, signaling that no values of x and y make both equations true simultaneously. The system is called inconsistent in technical terminology. Second idea. The infinite solutions case occurs when the 2 equations represent the same line. Geometrically, the lines have the same slope and the same y-intercept, so they coincide entirely. Algebraically, attempting to solve produces an identity like 0 equals 0, signaling that every point on the shared line satisfies both equations. The system is called dependent in technical terminology, with the second equation depending on the first by being a multiple of it. To recognize either special case before doing detailed solving, scan the 2 equations for structural patterns. If the equations have proportional left sides, but the right sides do not match the same proportion, the lines are parallel and the system is inconsistent. If the equations have proportional left sides and the right sides match the same proportion, the equations describe the same line and the system is dependent. The proportionality check is fast and prevents wasted work on systems that have no unique solution to find. Today we walk through one example of each special case to lock in both algebraic and geometric signatures. 2 special cases of linear systems do not have a unique solution. The inconsistent case has no solution because the equations contradict each other. The dependent case has infinitely many solutions because the equations are equivalent and describe the same line. Both cases have clear algebraic and geometric signatures. Here is the inconsistent case. Algebraically, attempting to solve produces a contradiction like 0 equals 5 or some other false numerical equation. The contradiction signals that no values of x and y make both original equations true simultaneously. Geometrically, the 2 lines have the same slope but different y-intercepts, so they run parallel forever and never meet at any point. Here is the dependent case. Algebraically, attempting to solve produces an identity like 0 equals 0, which is trivially true for any values. The identity signals that every solution of one equation is also a solution of the other equation, so the system has infinitely many solutions, all lying on the shared line. Geometrically, the 2 lines have the same slope and same y-intercept and coincide entirely. Step 1 in recognizing a special case. Compare the structures of the 2 equations. Look at the ratios of corresponding coefficients across the 2 equations. If the ratio of x coefficients equals the ratio of y coefficients, but is different from the ratio of constants on the right, the system is inconsistent and has no solution. If all 3 ratios are equal, the system is dependent and has infinitely many solutions. Step 2. If the proportionality check reveals neither special case, the system has a unique solution and any of the standard solving methods produces it. Always run the proportionality check before extensive solving work, because the check takes about 10 seconds and prevents wasted work on special case systems where there is no unique solution to find. The check is a high, leveraged diagnostic move on every system you solve. Here is the first worked example. Solve the system 2x plus 3y equals 6 paired with 4x plus 6y equals 20 using the elimination method and identify the special case if any. Step 1. Run the proportionality check. The coefficient ratios are 4 over 2 equals 2, 6 over 3 equals 2. The ratios of x and y coefficients match. Now check the constants 20 over 6 equals 10/3, not equal to 2. So the left side ratios match but the right side ratio does not. This signals the inconsistent case with no solution. Step 2. Verify algebraically by attempting elimination. Multiply the first equation by 2, 4x plus 6y equals 12. Now we have 4x plus 6y equals 12 and 4x plus 6y equals 20 as our two equations. Subtract the first new equation from the second, 0 equals 8, a contradiction. Step 3. Interpret the contradiction. 0 equals 8 is false for any values of x and y, so no values satisfy both original equations simultaneously. The system has no solution. Step 4. Confirm geometrically. Convert both equations to slope-intercept form. The first y equals minus 2/3 x plus 2. The second y equals minus 2/3 x plus 10/3. Both lines have slope minus 2/3 but different y-intercepts. The lines are parallel, never crossing, consistent with no solution. Step 5. Final answer: no solution. The system is inconsistent. The two parallel lines describe two different acceptable y values at every x, so no single xe pair satisfies both equations. So the system has no solution. The big lesson from this example is the proportionality check as a fast diagnostic for the inconsistent case. When the left side ratios match, but the right side ratio does not, the system is inconsistent and the algebraic methods will produce a contradiction. The geometric picture is two parallel lines, and the slope-intercept conversion confirms the parallel relationship cleanly. Always check for the special cases before extensive solving work. The proportionality check takes 10 seconds and saves the misallocated effort of trying to find a non-existent solution. Here is the second worked example. Solve the system 2x plus 3y equals 6 paired with 4x plus 6y equals 12 using the elimination method and identify the special case if any. Step 1. Run the proportionality check. Coefficient ratios 4 over 2 equals 2, 6 over 3 equals 2. X and y coefficient ratios match. Constants 12 over 6 equals 2. All three ratios equal 2. Left and right ratios all match. This signals the dependent case with infinitely many solutions. Step 2. Verify algebraically by attempting elimination. Multiply the first equation by 2, 4x plus 6y equals 12. The second equation is also 4x plus 6 equals 12. The two equations are now identical. Subtract 0 equals 0 and identity. Step 3. Interpret the identity. 0 equals 0 is true for any values of x and y. So every point that satisfies the first equation also satisfies the second equation. The two equations describe the same set of solutions, which is the entire line 2x plus 3y equals 6. Step 4. Confirm geometrically. Convert both equations to slope-intercept form. Both equations give y equals minus 2/3 x plus 2. Identical equations, identical line, coincident graphs. The dependent case is confirmed. Step 5. Express the infinite solution set. The solutions are all points on the line 2x plus 3y equals 6, which we can parameterize as x equals t and y equals 2 minus 2/3 t for any real number t. Or equivalently, every ordered pair x, y satisfying 2x plus 3y equals 6 is a solution. Step 6. Final answer: infinitely many solutions, all on the line 2x plus 3y equals 6. The system is dependent. The second equation is just twice the first equation, providing no new information. So the system has infinitely many solutions on the shared line. The big lesson from this example is the proportionality check, identifying the dependent case before solving begins. When all three coefficient ratios match, including the constant on the right, the equations describe the same line and the system is dependent. The geometric picture is two coincident lines lying exactly on top of each other. Recognizing the dependent case prevents the confusion that arises when a student attempts to find a unique solution that does not exist as such. The answer is the entire shared line, not a single point. 3 mistakes that catch every algebra student during their first weeks of special casework. Each one is fixable with a small explicit habit applied on every problem. First mistake: treating an identity like 0 equals 0 as the solution itself rather than as a signal of infinite solutions. A student running elimination ends up with 0 equals 0 and writes that as the answer to the system. The correct interpretation is that the equations are equivalent and the system has infinitely many solutions, all on the line described by either equation. The fix is to memorize the rule 0 equals 0 from elimination signals a dependent system with infinite solutions, expressed as the line equation itself rather than a single point. Second mistake: treating a contradiction like 0 equals 5 as if it were a usable equation rather than a signal of no solution. A student running elimination ends up with 0 equals 5 and tries to solve for some variable, getting confused. The correct interpretation is that the equations contradict each other and the system has no solution. The fix is to memorize the rule 0 equals a non-zero number from elimination signals an inconsistent system with no solution, written as no solution or the empty set. Third mistake: plowing into extensive solving on every system without first checking for the special cases. A student spends 3 minutes trying to solve a system that turns out to be inconsistent when a 10-second proportionality check would have flagged it immediately. The fix is to make the proportionality check the first move on every system, compare the ratios of the x and y coefficients across the two equations, and the ratio of the constants. If the ratios match, dependent. If left ratios match but right does not, inconsistent. If left ratios do not match, unique solution, and the standard solving methods proceed. The special cases of inconsistent and dependent systems appear constantly in real-world modeling, especially in engineering specifications, data analysis, and constraint-based optimization. Recognizing the special cases is essential for diagnosing whether a system has a sensible solution or whether the constraints need to be revised. 4 broad sectors below. In engineering and software requirements analysis, a redundant constraint is one that follows logically from other constraints in the system. Detecting redundant constraints is important for design clarity and for performance, because redundant equations add no information but consume computation time when the system is solved automatically. The dependent system test is the algebraic counterpart of redundancy detection, and the same proportionality logic applies. In contradicting requirements analysis, 2 specification clauses that contradict each other produce an inconsistent system with no solution. Detecting the contradiction early in the design process saves enormous downstream costs that would otherwise be spent trying to satisfy the unsatisfiable specification. Specification reviewers run proportionality, style checks on numerical requirements, and inconsistent systems flag specifications that need revision. In overdetermined systems, more equations than unknowns produce common cases of inconsistency. The data does not exactly fit the model, even though the model is reasonable. Statistical regression handles this case by minimizing the squared residuals to find the best fit approximate solution rather than an exact solution. The mathematical foundation of least squares regression starts with recognizing that the original system is overdetermined and inconsistent, then relaxing the exact solution requirement to find the closest approximate solution. In underdetermined systems, fewer equations than unknowns produce common cases of dependence. Many solution combinations satisfy the constraints, and the system has a continuous family of solutions rather than a unique one. Linear algebra handles this case through the null space concept, where the family of solutions is described by a parametric expression. The algebra level identification of dependent systems from today is the foundation for the linear algebra null space machinery in later courses. 3 things to take with you from this lesson today. The 2 special cases of linear systems are surprisingly common in real-world modeling work, and recognizing them quickly through the algebraic signatures and the geometric picture is an essential diagnostic skill for any system-solving work in this course or beyond. First, the inconsistent case has no solution because the 2 equations contradict each other directly. Algebraically, attempting to solve the system produces a contradiction like 0 equals 5 or 0 equals some other non-zero number. Geometrically, the 2 lines have the same slope but different y-intercepts and run parallel forever without meeting. The technical name for this case is inconsistent system, and the correct answer is to write no solution rather than attempt to extract values from the contradiction. Second, the dependent case has infinitely many solutions because the 2 equations describe the same line. Algebraically, attempting to solve produces an identity like 0 equals 0. Geometrically, the 2 lines coincide and every point on the shared line satisfies both equations. The technical name for this case is dependent system, and the correct answer is the equation of the shared line, expressed in any standard form rather than a single point. Third, always run the proportionality check before extensive solving work begins on any linear system. Compare the ratios of the x coefficients across the 2 equations, the y coefficients across the equations, and the constants on the right side. If all 3 ratios are equal, the system is dependent with infinite solutions. If the x and y ratios are equal, but the constant ratio differs from them, the system is inconsistent and has no solution. If the x and y ratios are different from each other, the system has a unique solution, and any of the standard solving methods produces it cleanly. The check takes about 10 seconds per system and prevents wasted work on special case systems where there is no unique solution to find. The proportionality test is the algebraic counterpart of the slope and intercept comparison from the geometric understanding of systems, and the 2 perspectives reinforce each other across every system you analyze. Recognizing the special cases is also important for real-world modeling work where contradictions and redundancies in a model often indicate that the underlying problem statement needs revision rather than that a solution should be sought. The diagnostic skill is therefore both a math skill and a modeling skill, and the practice today pays off across many later applied contexts. Coming up next, the lesson called 3 Variable Systems, where we extend the system-solving toolkit from 2 variables and 2 equations to 3 variables and 3 equations. The algebraic methods scale up cleanly with 1 extra elimination step, and the geometric picture extends to planes intersecting in 3-dimensional space, rather than lines intersecting on a 2-dimensional plane. 3 variable systems are the gateway to all of linear algebra and to the matrix methods used in computer graphics, scientific computing, and machine learning.